So sorry, you pushed the stop button instead of the pause button. So this is where I left off. You can check the previous video. I think I'm gonna call this one part B, and then I'll call the other one part A. So there's the shear equation, valid from 0 to 3. Let's get started with our moment equation. So for our moment equation, sum of the moments about where we made our cut, which is this point right here, equal to 0. Counterclockwise will be positive, and we start again from left to right. Let me see if I can zoom in here a little bit more. All right. So let's see where my limit. Okay. All right. So RA produces a counterclockwise rotation, so therefore is positive. It is 4 kilonewtons. It is a distance of x, so x meters. Then we continue, and this right here, which has a magnitude, and I'm going to write it again, of 4/3 x times x, which is this times 1/2, which is equal to 2/3 x squared. That is the magnitude of this guy right here. It also produces a counterclockwise rotation, so it is also positive. So this is negative 2/3 x squared kilonewtons, and this one's located at a distance of 1/3 x. If this is x, this is x over 3. So times x divided by 3 meters. And then nothing else. And last but not least, Rm, which is also counterclockwise. It is positive, equal to 0. We move these two guys to the right side of the equation, and the moment equation is equal to, let's clean this up a little bit. When it goes over to the left-hand side, it becomes a negative 2/9 x cubed minus 4x, and this is of course in kilonewtons meters. There you go, very nicely. Let me pause here and get these numbers in a spreadsheet already for you guys. All right, so just to show you exactly what I was doing in the last few seconds or last few minutes, I hope this comes out. I'm gonna move this. It's basically recording what I have on the desktop, and then I'm gonna move this other guy into place right here. So this is what I did. I went ahead and I evaluated from 0 to 3. In here I put the shear equation, and in here I put the moment equation, and these are the values for it. So I'm actually going to graph these so you guys have an idea of what they look like. Insert XY. There you go. And I think I'm going to do them separately. And I should. Let's see here. This right here is my shear. All right. And my moment. This is my X, and this is my Y. This one is my moment diagram. I'm going to put it right below it. starting to take shape. Now let's go back to this guy and continue. So I'm done with the very first section. Let us continue with the second section. And on the second section, we'll be making a cut somewhere in here. All right. So believe it or not, this one's going to be a little bit easier. It is usually those triangles that give us a little bit more of a headache. So we have RA with a magnitude of 4 going down. We have a rectangular distributed loading. It goes all the way up to 4 kilonewtons per meter. And then right here at B, sorry, made my arrow too big. RB has a magnitude of 22 kilonewtons. And then this is the part that interests us right here. We only have a section of our rectangular distributed loading, but that's okay. From here to here is 3 meters. From here all the way to our cut is our distance x. And of course, if this is 3 meters, this is x, this has to be x minus 3. There you go. Remember that our resultant for our rectangle is located 2 meters from point A, but 1 meter from point B. So we'll get to that in a minute. Let's go ahead and add our shear. We just add our shear, and we're gonna add our moment. Again, clockwise rotation for the shear and happy face for the moment. Let's go ahead and do our sum of the forces in the Y must be equal to 0. Up is positive, and this is only valid from 3 to 6. So, oh, I'm so sorry. From 3 to 6. Oops. All right. Sorry, I didn't look at my camera. There you go. This is only valid from 3 to 6. So let's go ahead and do some of the forces in the Y. Alright, it's -4. My distributed loading from my triangle, which is basically base times height divided by 2, or 1/2 4 kilonewtons per meter times this length, which is 3. And then of course we have our plus 22 kilonewtons from our RB. And then this guy right here. This guy also has his own resultant force. And its magnitude is 4 kilonewtons times this distance, which is x minus 3. And it is actually located half of the distance away from here. That's where it's going to be placed. Which of course doesn't interest us right now when we're doing our shear, but it will interest us when we do our moment, or sum of the moments. X minus 2 divided by 3. Right. So this guy right here, also going down, that will be negative 4 kilonewtons per meter times the entire distance, which is x minus 3 meters, minus v equal to 0. Put our v on the right side, and v is equal to, let's start cleaning some of this up. This is -4, 6, 22, and this one's a little bit, -4x plus 12. There you go. So v equals 2 negative 4x. And then clean that up a little bit. Gives us plus 24. And of course this is in kilonewtons. And this is the shear equation. Again, the one that's only valid from 3 to 6. Now let's work on our moment. Sum of the moments about our cut right here must be equal to 0. This is counterclockwise, positive. We start from the left, work our way to the right. That produces a counterclockwise, our RA, which is 4 kilonewtons. It is a distance from the cut of x meters. Our next one will be our triangular distributed load. It also produces a counterclockwise, which is positive, so plus 1/2 base times height, or height times base. And this particular guy happens to be located this distance right here. So if this is x minus 3 and this is 1, so x minus 3 plus 1 is x minus 2. It is x minus 2 meters away from our cut. And again, it's producing a counterclockwise rotation. Then our RB. Our RB produces a clockwise rotation. So that will be negative 22 kilonewtons. And it is a distance of x minus 3 meters. And last but not, second to the last, our counterclockwise rotation being done by our rectangular distributed load, which again, we already found this magnitude to be 4 times x minus 3. So this is 4 x minus 3, and it is located at a distance of x minus 3 divided by 2. This is, of course, kilonewtons meter. And now, last but not least, our moment m plus m equal to 0. There you go. Clean this up a little bit. That'll be leaving m on the left side of the equation, and flipping everything over to the right side will make everything negative. So, for example, this 4 times x will be negative 4x on the right side. All right. This, of course, will be 6 negative 6x plus 12 if you distribute this correctly. So I'm already over here. This is positive 22x minus, because this negative and this negative are positive, when you flip it over to the right side it becomes negative. So you can do it the long way yourself. 66, and this becomes a 2 quadratic equation. So I can go ahead and do this. Much better. And let's go ahead and collect like terms. All right, so went ahead and collected like terms, simplified it, and here is our moment equation, guys, for our second section. So I'm going to pause right now. I'm going to use Excel also, just so it can give me nice clean graphs for you to look at, and we'll be back right now. All right, going back to where we left off, I took a little bit of time, and from section 2 I went ahead and grabbed the shear equation and the moment equation, and I graphed those guys. Let's see, where is my screen? Oh yes, this is my screen. This is shear equation. There's the moment equation, and I went ahead and created another table right here. This one's from 3 to 6. So take a look at our shear diagram. And this makes perfect sense because our negative 4 is our RA, and if you remember correctly, it is 4 going down. This is our from negative 10 to positive 12 is a 22 jump, which makes perfect sense. This is our RB going up. So this is what our shear diagram looked like. Let's take a look at our moment diagram. Again, if you take the integral of x squared, you're going to end up with a cubic function. And this is what it looks like from 0 to 3. It goes from 0 to negative 18 kilonewtons meters. And then, of course, this one being a linear function, if you take the integral of that, you end up with a square function. And that's why this one is a negative 2x squared plus 24x minus 72. And as you can see, we also on this one start at 0 and we end at 0. So I just did the graphs just so I can show you that you can actually graph these in Excel. It just creates real nice, pretty graphs. Sometimes we can make errors in our calculator. Obviously, you cannot use Excel or a computer in your exam, but when you're doing your homework, this would at least test and ensure that you got the right answer. So I hope this video was of some use to you guys. I hope it helps. And tomorrow I will be working on some graphing methods. Instead of by equations, it's going to be by graphing. Well, thank you very much, and we'll keep communicating.